Hi everyone. Today's topic is logistic regression. This is optional topic for the people who have a dichotomous outcome for their research paper. So the students who do not have a dichotomous outcome variable don't need to watch this video, but this is actually kind of interesting topic. So maybe for the future purpose, you can watch this one, or you can keep it this video. Okay, when do we use logistic regression? Let's see. Yeah, so so far we have learned regression assumptions. Outcome variable should be continuous variable for regressions, right? But when you have binary outcome, for example, yes or no, or dropout, in this case, dropout or not dropout, or pass or fail, success or fail, this kind of two options in responses. Then you have to use logistic regression because some of assumptions are violated if you just conduct multiple regression in that case. So this is a special type of regression, which is logistic regression, should be used when you have a dichotomous outcome. Okay. All right. So here, this is one of the x variables. Maybe this is kind of score or other kind of thing, like given x has number one person has 1, number 2 person is 2, blah blah like that, and then this person, number 1 person didn't pass the exam, and number 7 person passed the exam. So pass was coded as 1, not pass, fail was coded as 0. Okay, so this is observations. So this is the observations, okay? And then you see on the x-axis so 11 people's x-score was coded like that. So intuitively, this is not linear at all. X-Y relationship, it's not linear. So this is like a S, almost, like S. So how can we run a simple, how can we run a regression with this strange looking XY relationship? So since XY relationship is not linear, it's simply violating linearity. So we shouldn't use a regular regression, okay? So, but we have wonderful options, to change this kind of strange S-curve into linear. How can you do it? We just simply change the scale. How can we do it? So instead of this S-curve, we have to change this curve into linear. So then we can run regression. So logistic regression means, in this case, this is just a regular raw scale. So this is x and this is pass. This is pass. So instead of using just the raw scale of pass, we can calculate the probability of pass. How can we do it? Based on this x, given x, we can calculate probability of pass for number 1 person, probability of pass for number 2 person, and probability of pass for number 3 person. So since they have a very low score on the x-axis, their probability of pass is very low, right? But somehow around this score, passing rates is kind of getting more and more, right? So once a person's threshold is higher than a certain number, then passing rate, passing probability is high. And also, this is only 2 options, pass or fail. So only 2 numbers, 1, 0 on the y-axis. So this exaggerated observations should be linear, stretch. So that's why we change the raw scale into logistic scale. So here, logistic regression. So in order to get to this point, we have to go through a couple of steps. First, pass raw scale should be changed into probability. And then we checked this scale, x versus y of probability is linear. We check that that's not linear. So we change this into this. So this is probability, and p over 1 minus p is called odds or odds ratio. Okay. So for example, if the probability of rain tomorrow is 80%, then what is p and what is 1 minus p? So p is 0.8 because 80% is percentage score. So if you change that, if you convert that into probability, it's gonna be 0.8. And what is the probability of not rain? No rain. That is 1 minus 0.8 equals 0.2. Okay, so 1 here, numerator p becomes 0.8. Denominator 1 minus 0.8 equals 0.2. So 0.8 divided by 0.2 becomes 4. So that means what? Simply, the probability of rain tomorrow is 4 times higher than that of no rain. That's what it is. Okay, so here the probability of rain tomorrow is 0.8 probability. Think about this scale. So this 0.8 probability turns into the odds ratio becomes 4 because 0.8 divided by 0.2 is, yes, 4. So the interpretation of odds ratio is the probability of rain tomorrow is 4 times higher than probability of no rain. Okay, and then we check this odds ratio or XY relationship. Then it's still not linear. It's still not linear. So we add one more. This ln means logarithm function. Logarithm function. We add a logarithm function here. Then it becomes linear. Now, if you treat this guy entirely as a y variable, then this y with the x will be linear. So now we're gonna use this logic function as our new y. So once you run the regression using this logic function, then you're gonna have same type of coefficient table, just like what you had before. in the multiple regression. And then just a little bit, just be careful about the interpretation because the scale has been changed. So when we interpret it, we convert this scale back into original scale, or we can just interpret it as it is. Okay, I will show the example later. Okay, anyway, what we are doing here is all about not to violate assumptions. Okay, I was just talking about only linearity assumptions here, but we have IID assumptions, right? Residual assumptions. Yeah. Once you convert this into logistic function, then we take care of every assumptions. Okay, so that's why logistic regression is very powerful. Okay. Also, in a different meaning, logistic regression is powerful because you know, the life is full of decision making. Life is full of binary outcomes. For example, whether or not a single woman decide to married or not, right? Or whether or not a couple decide to divorce or not, right? Or whether or not a student pass or fail an exam, or whether or not a businessman succeed in the business or fail. You know, many events or results can consist of only two outcomes, two, you know, responses instead of a continuous variable. Or when you have a math scores, yeah, usually math scores, yeah, it's continuous variable, but let's say the school try to decide a recipient of scholarship based on the math score. So a threshold will be given, right? And then let's say the threshold of the scholarship is 60. So from 0 through 59, they are all coded as 0, not recipients. And the people who received 60 or higher than 60, they will be coded as 1. Only two choices. So the students who have 60 and the students who have 59, they're just 1 point different, but the outcome is completely different, right? The consequence is completely different. One is a recipient and coded as 1. The other is coded as 0, right? So logistic regression is very powerful and useful. Okay, so why this thing is cut here? Let's see. Okay, strange. So here, logistic regression, logit, p over 1 minus p, beta 0 plus beta 1x. So this logit function equals beta 0 plus beta 1x. So if you wanna remove this logistic logarithm function, what would you do usually? You plug this entire thing in the exponential function, right? So then this logit and exponential are removed. Then now what you do? P over 1 minus p equals exponential parenthesis beta 0 plus beta 1 xi, okay, where logit of the raw score is dependent variable. So this entire left term is the dependent variable, but if you want to reinterpret this and you can make it exponential, then you're gonna have p over 1 minus p as the dependent variable. Does it make sense? Well, anyway, remember, logistic regression is satisfied with linearity function, linearity assumptions, okay? Odds ratio violates the linearity assumption. Probability definitely violates the linearity assumption, but logistic, log odds or logit, we call it log odds or logit. This guy is satisfied with the linearity assumption. So in the right term, you're gonna use regular regression formula here. This is population equation, right? Because we see these Greek letters, beta 0 for y-intercept, beta 1 is for what? Slope, okay? Okay, so as I said, in the logic function, ln p over 1 minus p, if you want to get rid of this logit, you said plug the exponential, plug the whole thing in the exponential. So exponential here and logit, they are removed. And then you saw the, beta 0 plus beta 1 x1 here, right? If you plug them into exponential function, then you will have this one. You will have this one, okay? We have this one. So odds, this part is odds. Odds equal an exponential function of a linear equation. What is a linear equation? Linear equation means logit ln p over 1 minus p, okay? So a feature of the exponential function is that, so exponential function a plus b addition rule becomes multiplication like that, okay? Minus inside the parentheses become division function like that, okay? All right. So once you get this one here and you see this one inside the parentheses, you have addition. If they are getting out of the parentheses, it becomes multiplication. So this is y-intercept, this is slope part, okay? So if you have x equals 2, you plug x here 2, then you will get this one. If you have x3, x equals 3, then you plug 3 and you have this. Now, this is logit. This is logit function, okay? And this is estimated regression. So instead of population equation, you use alphabetical letter B0 plus B1. This is estimated regression equation based on sample data, okay? And I said this is a linear model, okay? So this is familiar for you, right? You think this is the entire y, new y. Let's say y equals b0 plus b1x. So sounds familiar, right? So let's think about this logistic function as y, okay, new y. all right? So new y equals b0 plus b1 x1. So this is the coefficient table in logistic regression. So constant y-intercept is minus 6.347 and x-slope is 0.984. Okay, you're doing the same thing as if you did in the multiple regression, right? Using coefficient table, you make the estimated regression equation, right? It's the same thing in the even logistic regression, okay? And also here, p-value. So x variable, p-value is 0.076, which is larger than alpha, 0.05. So what can you say? This x variable is not statistically significant, okay? But one thing here, wild. This is a wild test, not t-test, wild test, okay? So in logistic regression, we use it wild test instead of t-test, okay? But same interpretation, just like what you did using p-value in multiple regression. Here, p-value and the alpha level 0.05, okay? So this is interpretation in the logistic regression. So we know B1 is 0.984. How can we interpret it? So one score increase in X. When one score increase in X, so in 1 unit increases in X, the expected logit, because this Y is logit, okay? So the expected Y logit of passing increases by 0.984. So you just change this word instead of Y when you interpret logistic regression results, okay? It's exactly the same as the simple regression interpretation. Do you remember that? Okay. If you have one more x variable here, what do you do? Comma, controlling for all other x variable, okay? So if you have x2, you plug this x2 here, x2, 2 in this x, then you will have this number. If you have this for logit, the logit itself is y, okay? If you have 4, plug 4 in this equation, then you will get this one, okay? All right, so this is not complicated. This is not complicated at all. So you started pass or fail, row scale, right? And then you find out pass or fail, this dichotomous variable violates linearity, xy linearity relationship, right? So we convert that into probability, okay? So instead of a pass or fail has only 2 responses, 0 or 1. But if you calculate probability, it's kind of continuous variable, right? But we cannot use this for regression because it is still violating linearity assumption. So what we're gonna do is we add odds using p. So what is odds? 1 p over 1 minus p is odds, right? So p over 1 minus p, p divided by 1 minus p, okay? So this exponential of logit, so this is cancelled out, right? So then it becomes just odds. Anyway, so if you calculate the odds, you get this number given x values here. And then we also know this odds also violate what? Linearity assumption. Well, any kind of assumption, yeah, that violated all the assumptions, okay? Like IID assumption. Then in order not to violate that, those assumptions. We do one more steps. How? We change this odds into logistic function. Then the logic function has this kind of linear equation. Okay, so if you plug 2 to here, you got this one. If you plug 4 to into x, then you got this one. This is logic. Logic itself is y. Okay, here. Okay. So here, this is x variable 1, 2, 3, 4, 5, 6, 7. Maybe here ID 1, 2, 3, 4, 5, 6, 7, 8, something like that. So x score between 1 to 6, 1 to 5, all the students passed or fail. 0 is coded as fail, and 1 is coded as passed. So once a student has more than 6 or 6, so it's, you know, the observations looks like a pass. But since this is people's decision, people's evaluation, so this student, even though this student has a higher score, he still failed the exam or whatever. So what about this? This is probability, passing probability. So since this is a high, probability is high. This is calculation, okay? And probability is calculated by the SPSS. Based on this probability, and then estimated probability. So this is observed probability. I mean observed outcome, pass or fail. But this is estimated result, not observed result. Okay. So this is a fail. This is a pass. Does it make sense? And how could we do it? Logistic regression. Analyze, pull down menu, you see analyze and regression. And here binary logistic. Then you will have some optional window here. And here x is x here. And the y path is here, dependent. Okay. And then you click save button. Then you will see these options and probability and group membership. So include the covariance matrix. So click this 3 and then continue. And option, and then classification plots. Each step include a constant in the model and continue. So you will have the outputs that you need to interpret. So again, this is called odds, okay, or odds ratio, odds. How can we interpret it? So one unit change in x is a factor of exponential beta. When we discuss odds, we are talking about how many times more likely one event is than another. So I use the example of probability of rain tomorrow. So how many times? 4 times higher than the probability of no rain. If the probability of rain tomorrow is 80%, okay? So here, how can you interpret it? So here, this is it. In this case, pass or fail example. So here, this means you plug this x here, and the exponential x equals this guy. The person is 2.676 times more likely to pass than fail for every added point on x. However, you see this p-value is not statistically significant, so you can ignore this interpretation. So this person in consequence, in conclusion, you say, this person wouldn't be 2.676 times more likely to pass than fail because because of p-value is larger than alpha 0.05. So actually, the passing rate is not higher than the other people. Until now, we have used t-test, but in logistic regression, we use wild test because the distribution is not followed with the t-distribution. Instead, logistic regression follows wild test. Wild test is kind of chi-square distribution. So anyway, beta equals 0. This is null hypothesis, and the test value is a t-test for, this is just regular regression. And f-test, for regular regression model test is this, the t-square, okay? And t-statistic equals b over standard error, okay? But this is not working for logistic regression. Why? Logistic regression follows wild test, which is a type of chi-square test, okay? So wild test. So what kind of wild test? I mean, the wild test shows what kind of distribution. So when degree of freedom is 1, this looks like it. Looks like a chi-square test. If you have more degree of freedom, then it looks like this. But still, it's not like t-distribution. T-distribution is really similar with the z-distribution, right? Like a normal distribution. But wild distribution is just like a chi-square distribution. So this is a chi-square distribution is not symmetric, right? Yeah, if you cannot use a p-value, well, you can use statistics also, right? Not t-statistics, but wild test. So wild test is chi-square, kind of chi-square test. So users type chi-square test with a specific degree of freedom, then you will see this kind of table. In the earlier video, I explained how to search t-test value in the Google, right? It's the same way. You just type chi-square value with this degree of freedom, and then you can get it. So here, degree of freedom is 1. At that time, chi-square statistic critical value is 3.84. So since this wild test value is smaller than 3.84 critical value, it is not statistically significant, which is congruent with this result, p-value. And so the importance of the sample size. So because, let me show that to formula. So here, this is standard error. This is B slope. So if your B is big, then your wild test value become large. So it's likely to reject the null hypothesis in that case. But if your B is small, then since wild test value becomes small, you will be less likely to reject the null hypothesis, right? How about the denominator? If a denominator standard error is large, entire value becomes small, so you are less likely to reject the null hypothesis, right? Anyway, what I try to say is when your standard, when is standard error becoming big. So standard error, when standard error is big, that means that your sample size is small. Okay. If error is large, your sample size, that means your sample size is small. If your sample size is small, this whole number, if your sample size is small, error become large, denominator become large. If so, the entire value becomes small, right? If the denominator is large, the entire number is small. If it is small, it's less likely to reject the null hypothesis. So here, small sample size, less likely to reject the null hypothesis. Small sample. Large sample, small error. If small error, the entire number of t-statistics or wild statistic become large. So it's more likely to reject the null hypothesis. Okay. Much as we did for MLR, multiple linear regression. We have several ways to evaluate overall performance LR, logistic regression. So do you remember model test, model summary? We use R-square, right? Here we have some kind of R-square, but since this is not real R-square, we call it pseudo R-square. Pseudo R-square. Two kinds of pseudo R-square are detected in the SPSS. So Cox, Snell R-square, Nagarski R-square. So you can use the same rules of thumb. Cohen's rules of thumb. Remember that? So R-square, this is pretty high, right? Cohen's rules of thumb. Do you remember that? All right, so this is a very large number, okay? You can report both of them for model summary. And then what? You show this one. Coefficient table is this. You report this, okay? And p-value, okay, you report this. Yeah, interpretation is pretty similar with this multiple regression, right? And here, whenever you add more x variable, the R-square is substantially increased, right? So regardless of the importance of added x variable, whenever you add a new x variable, it's gonna R-square becomes larger and larger. But if the change is not that much, then you shouldn't add more x variable, because you know your R-square substantially, should be increased whenever you add a new x variable. Otherwise, you shouldn't add a new x variable if they are not improved dramatically. Okay. All right. This is the last slide. Okay. The end. Thank you.